I wasn't expecting quite this many people to be interested in Java performance, but that's great. I'm glad you're here. Before we get started, everyone in here is a Java developer, I assume. Is that right? Anyone who's not? Okay, what do you code, just out of curiosity? Oh, you're an architect. That's even better. Good. Well, we will actually cover a little bit of architecture. That's why I asked that. This is actually like an hour to 3 hour presentation. So I'm going to go through this rather quickly. So what I ask you to do is, if you have a question, please ask it. Because I'm going to go through some parts of this very quickly. And from the description, you probably saw that there's a significant part of this which focuses on like kind of low-level code and stuff like that. I'm going to spend a little bit more time on that and spend a little bit less time on the architecture and all that kind of stuff, okay? So again, the important thing there is if you have a question, please ask it. I'm happy to answer it. My name is Pratik Patel. I work at Azul Systems. How many people have heard of Azul before? Wow, that's only half the people. All right, good. So I'm a Java champion. I'm based out of Atlanta, Georgia. We put on a nice community conference there out of the Atlanta JUG called Dev Nexus, which is in the first week of March. I encourage you to come and check that out. We get about 1,500 people, and we have things that you don't have here, like chicken and waffles. So please come check that out, okay? And the other important thing on here is that you can reach me after the session at PR Patel on LinkedIn, Blue Sky, or X. Does anyone still use X? I don't use it much, but I check DMs occasionally. Okay, never mind. So I do work at Azul Systems, and what we do is we make Java virtual machines. We have a 100% free and open source one that gets hundreds of millions of downloads a year called Zulu. It's completely free and will be free forever. And then we have a high-performance Java VM called Azul Platform Prime. And we also have this new thing, since most of you are Java people in here, called Code Inventory, which is like X-ray for your Java applications. It actually tells you what you're running in production, so you can figure out what code you're not running in production to help you reduce your technical debt. Okay, and that's pretty much all that I'm going to talk about. But if you have a question about any of these things, I'm going to be here all day. And I'm happy to answer that and give you a demo of this or some of the other stuff. All right. And then we also host this thing called Fuje, which is a community platform where you can be an author. We have lots of different authors around the world that publish stuff on it, but you can check that out. We do some live webinars and stuff too. Okay. I'm going to talk a little bit more about performance, but again, our high-performance VM is a drop-in replacement for OpenJDK, and most of our customers see 20% plus performance gains out of the box, and if you're running big data infrastructure like Kafka or Cassandra, you see even better improvements. It's true high-performance VM. And we'll talk a little bit about like how that works as we go through this to give you an idea, but I'm not going to spend too much time on the product side. This is more for you. And you might be wondering, why should you listen to me to talk about Java performance? I work at Azul. We make the fastest JVM. And I also led the Java performance team at a telco in the US called AT&T for 7 years. So I have a lot of experience, hands-on experience doing performance tuning, both on the small with code and large at like the architecture infrastructure level. All right? So again, if you have questions, please ask them. I have a question for you, though. What's the one trick to make Java apps run faster? Anyone know? What's that? Upgrade the Java version. That is actually a good answer. A better answer would have been use Azul Platform Prime, but you know, it's close enough. This is actually true, right? And this is a little bit of a trick question, of course. But if you're, for example, if you're running Java 8 or Java 11 and you go to 21, you get a big performance boost just by upgrading the Java version, which a lot of people don't know, because what happens is the OpenJDK is continuously improved. Every year it gets better and better in terms of performance, okay? So that's probably the easiest way to do it. And of course, this is a little bit of a trick question because there isn't really one answer to this. So we're going to cover some of those different things in this session to give you an idea of what you can do to make your Java apps performant and better and things like that. But if there is one true answer to this question, that is keeping things simple is probably the best thing to do, because I'm a software developer just like you, and what I find myself doing a lot is I like to make things overly complicated, like every other engineer, right? You want to write more code or you want to make things more sophisticated, and you end up making things more complex. So I always have to remind myself to, especially when it comes to performance, Try to keep things as simple as possible to get the most out of your application and the JVM and the hardware and everything that you're doing. And so corollary to that is, and again, this is something I tell myself all the time when I'm writing code, which is try not to be too clever. Try not to make your code too complicated. You know, you're always on the hunt as an engineer to do optimizations. And you've probably heard the saying, the root of all evil is premature optimization, right? So try not to do that. That's, if nothing else, hopefully you get that, right? Don't optimize prematurely, okay? So these are the topics we're going to cover in a few minutes. We're going to talk about system design first, because I think this is probably the most critical aspect of Java performance. Now, everything depends on what kind of application you have. If you're writing Spring Boot applications, which are basically a backend to a website, you have a different set of challenges as opposed to if you work in financial services or fintech and you're doing something like high-frequency trading. At Azul, we have a lot of customers that do a lot of both, but a lot of the people who use Prime are doing high-frequency trading, and they want that really low latency and stability at scale, and that's where a lot of system design comes in, okay? But this is what we're going to talk about. We'll talk about code profiling, finding bottlenecks, spend a little bit of time on coding practices, spend a little bit of time on caching, because obviously everyone knows caching is a great way to boost performance, and then we'll round out by talking about memory and garbage collection, and hopefully try to finish on time. Lunch is after this session, right? Is that right? You don't mind missing lunch for this, right? Okay, I'm just kidding. I found that if you let people out early before lunch, you get much better reviews. I don't know why. Go figure. Okay. Anyways, scalable architectures. Let's talk about this for a minute, because again, I think this is one of the key concepts that a lot of people overlook, especially people who are newer to software development. Now, when I think of the app spectrum, we kind of go from left to right on this, right? Everyone has probably built microservices or is looking at building microservices. Everyone has probably worked on a monolith. And then there's probably some people who do functions as a service, or what's known as cloud functions. But I like this diagram because it summarizes the overall choices that you can make either as a developer or as an architect in terms of how you build an application. If you're unlucky, maybe you've inherited an application. If you're even more unlucky, maybe they've asked you to re-architect an application into microservices, which is extremely difficult, as you know, okay? But the key aspects of this slide here are what are on the bottom here, right? If you're running a monolith, you're essentially doing what's called vertical scaling to scale out an application. Now, everyone's heard of horizontal scaling, which is on the right side here, right? Horizontal scaling is basically you add more servers like this. So you start with 1 or 5 servers, and as you need more capacity, you add more servers. You have a load balancer that distributes between those servers. That's how you get more scale, right? So what's vertical scaling? Vertical scaling is having maybe a server or a small set of servers, and you add more CPU and you add more RAM to it. So that's vertical scaling as opposed to horizontal scaling. Now, it's much easier, obviously, to do horizontal scaling because it's easier to add a new instance or a server or node to something as opposed to adding more memory to a server, or taking your application off an existing server and moving it to another server, which obviously takes a long time. Not anymore necessarily with what you can get on the cloud, right? You can go from like a Amazon AWS XL to an XXL instance pretty easily, but you have to migrate your application to that, and then you have to do some configuration and stuff. But the reason why the tags on the bottom, not elastic and very elastic, are for that reason. It's harder to add more capacity, CPU and RAM, to an existing server than it is to just add a new server to an existing cluster, okay? So in terms of performance, again, if you've inherited an application and you're running on a monolith, your only option may be to do vertical scaling. If you're running on microservices, then you can do horizontal scaling, which gives you more elasticity and gives you the capability to scale much, much easier. And more importantly, this is one of the things that I talk to a lot of Azul customers about, which is it's great to be able to scale up. What's the problem with adding a whole bunch of servers to your application? You have to pay for it, right? Especially if you're running in the cloud. And that can get very expensive. So the elasticity here is important because as you scale up, at some point in time, you may also want to scale down. For example, if your load goes up and down during the course of a day, you may need less capacity, but you don't want to pay for it, right? That's commonly known nowadays as something called cloud cost optimization. So if you're interested in that specific topic, I actually have a full presentation, hour-long, that talks about techniques for cloud cost optimization to help you save money. So, you can add servers in horizontally like this, but how do you scale back? And what are some of the things that you have to do to be successful for having right sizing for cloud deployment? So if you're interested in that, please hit me up. I'm happy to do that remotely or in person, okay? All right, so this is also a little bit of a trick question, but which architecture is the most efficient? What do you think? If you look at this diagram right here, right? When you think of efficiency, which one of these architectural styles do you think is the most efficient? What's that? It depends. Hey, only I can say it depends, not you, okay? Stop that. Okay, so again, this is a little bit of a trick question because the answer actually is, if you're looking for pure efficiency, the monolith is actually the best way to do it. Running everything in a single process as opposed to having things distributed. Microservices are all the rage right now, but what's the performance impact of a microservice? Let's say you have 10 microservices. You have a lot more, obviously, but just for the sake of this mental exercise, say you have 10 microservices. What you're doing is this microservice calls this one, which calls this one. And every time you make a hop between a microservice, what do you have to do? You have to take your data, you typically serialize it to JSON, and then you have to deserialize it to JSON. Now, that has a huge number of performance impacts. Number one, you're transferring stuff over the network. Networks are very fast, but you still have to do that. You have to pay overhead for taking Java objects, converting them to JSON, and then unconverting them from JSON back into Java objects. And all that adds overhead. Normally, it can add anywhere from 10 to 30 or even more % in terms of overhead. So the best and most efficient way to write an application is essentially to have a class and do class.method within the same, essentially, process within a JVM, right? But that doesn't scale from a number of different reasons. We talked about vertical scaling versus horizontal. And plus, the other thing is it doesn't scale from a code and team perspective. You can't have a whole bunch of developers working on a giant monolith. Actually, you can, right? How many people work on a monolith here, just out of curiosity? Okay, so I'll pick on you in the green shirt. How many people are on your dev team that work on that monolith? Okay, see, that's small. He said 9 people. Anybody else have more people working on the monolith than 9? No? Okay, that's good. Well, when I used to work at AT&T, on any given part of our application, which is a monolith, we had like 30 or 40 developers working on it. You can imagine the headache in terms of doing merges and pull requests and all that kind of stuff around it. It basically slowed the overall team's velocity down because everyone was funneled into a single code base because it wasn't modular. It was just a monolith, right? It makes sense to you probably if you've done monoliths and microservices, or at least you can understand that. Okay, so that's the most efficient way to do it, but it's not the most scalable. The most scalable is the vertical scaling that we talked about, right? So all this plays into how efficient and how scalable is your application. It's up to you, and yes, someone said it depends. It does depend on what you can do with your application in terms of those things and how efficient it is based on your architecture. So we're not going to spend too much time on this because we want to get some more fun stuff. But again, there's no best performance architecture. Okay, so we've already talked about all this, right? Elastic gives you cost control. You can scale up and scale down dynamically, or what's called dynamic elasticity. And then, if you're using Kubernetes, that opens up a whole new world of different complexity that you have to deal with. I personally don't like Kubernetes too much. I prefer to use something like containers as a service, where you just go to Amazon Fargate or Google Cloud Run or Azure Containers, and you say, here's a Docker file, just go run it for me. And it goes and does everything and scales it up and down, right? So that's an option that you have, but you end up paying more for that added service that you get from cloud providers, unless, Are any people running OpenShift, for example? Okay, I figured there'd be a bunch of people, right? And OpenShift is a great product, but again, it's a lot of complexity. It gives you the ability to scale horizontally and do scale up and scale down. But again, it does come, nothing in life is free, as they say. Okay? All right, so I wanted to drop this real quick in here to give you, just to let you know that I'm not just completely making things up. When I say that monoliths are the most efficient way to run applications in terms of energy and like kind of straight throughput point of view, there was this post on X. This is about 18 months old, but the key point is here at the bottom, which is what they did is they basically went from microservices and compared that to running in monoliths, specifically modular monoliths, which is something you probably have heard of. And they did a performance study on this, and they found that latency and cost can be reduced dramatically by not doing microservices, right? So if you've been in this world for a long time, like I have, basically been writing software applications for a long time, you know that everything that's old becomes new, and it's like a circle, right? So, for a long time, everyone was like, yes, you should do microservices. That's the way forward. And now people are realizing that microservices are very complex and add a lot of overhead, and that impacts overall performance and cost. So some people are swinging back towards the monolith style, but not necessarily straight monoliths, but something called modular monoliths, okay? But if you're interested in this, I have a link to this at the end of my presentation. You can go read this article. It's actually a really good read to understand kind of the bigger picture when it comes to how to design and build an application, okay? So we'll talk about these things in a little bit more detail. A lot of the ideas in terms of how you should structure an application depends on what kind of scale you're looking for, what kind of latency can you tolerate, do you need both those things, are you more interested in throughput, right? So all these things play a big factor in this, okay? All right, so let's move swiftly on and talk about code profiling and bottlenecks for a bit. All right, so in terms of profiling tools, you've probably heard of most of these. There's Visual VM, IntelliJ IDEA Profiler, which is built right into the IDE, and also Java Flight Recorder. So when I'm doing performance analysis, either on my own project or for an Azure customer, these are the tools I typically reach for, but typically it's the second one, which I'm going to show you very quickly, right? So how many people have used IntelliJ IDEA Profiler before? Anybody? Okay. So a bunch of people have used it, so I won't spend too much time on it. But for those of you who haven't, I just want to show you what it looks like and how you can work with it. Now, what I did for this is, and I can actually run the demo, but I don't have time to do it, so I'm not going to bore you with trying to run a demo in front of you right now. So I just took a bunch of screenshots. So I used JMeter to drive the Spring Pet Clinic application. If you're not familiar with that, Spring Pet Clinic is the reference or demo application from the Spring people that they maintain themselves. So it's a good kind of demo application for stuff like this, right? And it also includes a JMeter test plan. So I started up Spring Pet Clinic, I opened the test plan, and I pointed it at it, pointed JMeter, which is basically something that you use to generate load for an application, at the Spring Pet Clinic, and then I hooked that into the IntelliJ Profiler, right? And as I was working through this to find some good examples recently, I actually found this example, which is kind of interesting. So again, using JMeter to run load test, the IntelliJ Profiler to profile the application. In this case, I just had it running locally, but with IntelliJ Profiler, you can connect to a remote JVM running somewhere if you wanted to also, okay? But what I found here is that as I was profiling this, on the top right here, let's see if my pointer works. Does that work? Yeah, there it is. Okay. When I was looking at this, this is the heat map type of diagram here. But if you look, you can see that there's this one operation called find owner, which as part of the JMeter test plan, you can see here's find owner. So I basically tried to connect the dots to see what kind of performance bottlenecks there were in this application based on this specific load test that was being run. And I found this find owner in here, and I thought that was a bit odd. It's like, why is a lookup to find a single database record this slow, right? You think it'd be really, really small. These other ones, like process form or show owner, which goes and pulls data. Why is the find owner taking so long? So as I drilled into this, and again, I don't have time to do a demo of this, but if you look at the bottom of this screen, this is a nice blog from someone at JetBrains that walks you through this. So if you're not familiar with this tool, you can have a look at Mala's blog, and she walks you basically through how to use this. So getting back to her example here, you can see that the find owner here is taking more time than I thought it should. So I drilled into this, and I pulled up the stack frame, and as I started to inspect this, what I found was that the find owner method is spending 10% of its time getting the local date, right? And that's where it's spending most of its time. Because what happens in this case is because everyone in this room is probably familiar with Spring Boot and Spring, right? And the Spring data and all that kind of stuff. So because this thing is being hit repeatedly, I know it's being cached. So why is it that every time that this find owner, and there's only about like 10 records in here in the data set. So I know it's being cached for sure, right? So I have, and that's why I have this in orange right here, right? It's important to understand the context of the overall application and what's happening. So in this case, I knew that I'm using Spring, and I'm using Spring JPA, and Spring JPA uses Hibernate by default, and Hibernate by default also has some level of caching turned on, right? So why is this taking so long? And as I start to dig into here, you can see that this is going and spending a lot of time getting a date. Now, unfortunately, this specific code branch here, I don't know, it's a little small. Let me zoom in for you, right? So if we zoom into this code branch right here, you can see here's find owner. Oh, let me move over a bit. Here's find owner, and somewhere inside of the Hibernate code base is going and grabbing the local date for some reason. I'm not sure why, right? Because the owner probably has a creation date, but why does it need the local date? The problem with this specific branch of code is that when you go and try to get the local date, it goes into the operating system and grabs the local date, and because of synchronization issues with dates all the way down into essentially the CPU and the CPU clock, there's a little bit of locking that happens, and that's why this shows up, okay? Now, the point here is not to pick on this example, but the point is to show you how I do profiling and try to find bottlenecks in code, right? I like using this specific tool. Java Flight Recorder is actually very good, but I don't feel it's the user interface is quite as nice as what the IntelliJ IDEA provides, okay? So anyways, just a quick example of doing some kind of profiling and the kind of process that I use. If you're using this, you can right-click on something and you can see you can go from the heat map that's up on the top, and you can drill into the method call stack, and then you can drill in and see what kind of time this is actually taking, and you can see the time is actually listed right here, right? So most of the time of the 151 milliseconds of this call, the 10% of this 1,500 milliseconds is spent just pulling up the local date, which is a performance optimization. If I want to go and monkey with that, I'm sure there's something in Hibernate. Actually, there wasn't anything in Hibernate that I could have used to sidestep that, but I'm sure there's a workaround for it, okay? All right. So one thing to note, though, is if you do use a profiling tool, it always adds some overhead. So this is a case of where the test actually can change the results of running your application. So you have to be careful how much you profile, especially if you're using something like Java Flight Recorder. When you say, I want to look at this, this, and this, and this, the more things that you have an instrument to collect profiling data for, the more overhead it will have, and the more it affects your overall test. So you just have to be aware that profiling does add overhead, and it's not completely clean. And because of that, one of the things that I like to do, especially for production, is do thread dumps. Now, you might be wondering, well, how can thread dumps help with finding performance bottlenecks? Actually, they can be really useful, especially on production, because it's nice to be able to run something like this locally or on a test server or something like that. But I'm sure that everybody in this room has probably hit some kind of issue or bug or performance thing that only happens where? On production, right? Everyone in this room. Right? So what do you do in that case? You could hook a profiler up to it, but again, you have to worry about this. The profiler adds overhead and changes the shape of how your application is running in some ways, right? So it can lead to a lot of dead ends. But thread dumps, however, can work really well for this, in my opinion. So what I typically do is I take a thread dump at half a second, 1 second, 2 second kind of intervals, depending on what kind of granularity I'm looking for, and then I feed them into a tool that allows me to compare different thread dumps next to each other. Then I can see where specific threads are spending some time in between thread dumps. So it's very easy to actually find problems like that, which I would say are, in English, we use the word low-hanging fruit. Hopefully that translates. Basically find the easy problems using thread dumps. And usually that's more than enough. But thread dumps are a good way to do this. It's again, the tool that I specifically use is called jstack.review. It's just a website. It doesn't send anything back to the server. It just loads in your browser, and you just load it up with thread dumps, and then you can compare different thread dumps to see where threads are getting stuck or where they're spending more time than you would expect, right? Again, a lot of this is couched on your application. Where does your knowledge of your application will help you understand, is this something that's really a problem, or is this just a database issue, right? So if you take multiple thread dumps and they're always showing that they're at some kind of database operation, you drill into the stack or the method call list, and you see it's like some kind of big query, you know that's your application, so that you know that this specific query always takes a long time. So you can say, okay, we know that takes a long time. We'll try to optimize that query, but you can find other things that you wouldn't expect to take time by taking these concurrent thread dumps or sequential thread dumps and comparing them. Okay. So, and I have a link to JStack.review at the end of these slides, so you can find the references there. Okay. So again, instead of profiling, I like to spend more time looking for bottlenecks because looking at profiler data and hooking up a profiler and figuring out where you should put in your profiling hooks and then running the profiling, it adds overhead, and a lot of times you end up at a dead end. It's not really helpful, right? So I prefer to find bottlenecks rather than doing true profiling, and I find, for me personally, that it's 10 times much more effective use of my time to find optimizations, to look for bottlenecks, as opposed to spending a lot of time just doing a low-level profiling, okay? Right, and so here's an example of JStack where I passed it a couple of different threads, and it will show you color-coded in between thread 1 and thread 2. Right here, for example, what is the difference between the first thread dump and the second thread dump, and you can see that this has changed where it is, and it can help you do that. And the way you take a thread dump is you can use JStack, or you can send a kill-3 command to a Java process ID. I don't like to use the kill command because it's way too easy to forget that -3 and just send a kill command, right? And that's a problem. So I prefer to use JStack to do that, because sometimes when I'm looking at a performance problem on production, it might be 3 in the morning and I may not be 100% awake, right? So anyways, I prefer using JStack rather than kill-3. But essentially you dump this into text file, and then you just upload it into this JStack review, and you can do this on production, which is great. Okay, so, and I'm going to get next time I come, I'm going to print up a bunch of these T-shirts. So, right? I mean, who writes test anymore? You just test on production. That's what it's for. So, okay. All right, so thread dumps versus profiling. Let's round this out quickly. Is that you can run on production with near zero overhead by taking thread dumps. And again, depending on your application, you may want to take a thread dump every half a second, every second, 5 seconds, etc., depending on what you're doing. 300 seconds is probably too long, but again, it depends on what you're doing. And that's a good way to actually find bottlenecks in production. All right. So another tool that I like to use, and this is something from Azul, but it's 100% free. It works on every JVM. It's called JHiccup. It's a tool for finding JVM jitters and pauses. Now, what this JHiccup does is it measures any kind of pauses that affects a running JVM. And the pauses could be from anything. It could be from something within your application, something in the JVM like garbage collection, not garbage control. Or it could be something in the operating system, right? It could be anything. So you have to figure out what is causing a specific pause. But once you have this data, you feed it into a tool called Histogram Log Analyzer, which is another free tool. And the way that JHiccup works is it basically sleeps for a second, wakes up, and records the last time it went to sleep. That's it, right? But this is surprisingly useful, right? Let me show you a chart. So the way JHiccup works, again, is it sleeps for a second and records the time, and that's all it does. But you take that data and you feed it into an analyzer like the histogram log analyzer, and then based on clock time, you can see when there were pauses in your JVM. Okay, this is another way to look at it, but basically it's the same as this. Oh, sorry. Skipped ahead, right? It's basically this, but in a little bit more detail, right? So again, every 1 millisecond, it says, here is, this is what time it is. And if there's a pause, the time will be off by a little bit instead of 1 millisecond. So the way that you use it is a Java agent. And I know a lot of people don't like running Java agents because they add overhead, and I 100% agree with that. But thankfully, JHiccup is a very, very, very low overhead, right? Your VM won't even notice it's running because it's not really doing much. But this is how you run it, right? So for the Pet Clinic application, if you run it like this is how you would do it. Okay? So this is the output that it produces. right? So this is in histogram log analyzer. So you run JHiccup for a while. Typically, I will run this on a customer's production application for like a few hours or a day, right? It's not something that you run in a short amount of time. I like to run it for a long amount of time so I get a full picture. It takes a while to convince somebody to run something in production anyway, so I want to get as much data as possible and get a full picture, right? But when you look at this, you could see that there were some spikes in terms of how long there were pauses in the VM for things, right? Unfortunately, I don't have a better way of saying that. But one of the things that I'm able to do with something like this is I can correlate these spikes to garbage collection, okay? Now, at the bottom, the x-axis here is elapsed time. So you do have to make a note of the time that you start an application as precisely as possible. That's easy to do, right? You basically just say, what's the time, and then go run your Java application. It'll get printed into the console, or you can pipe it into the log file so that you have a permanent record of it. So this is elapsed time, and then you can look at other logs, or you can look at other things which are happening within your application and do essentially a correlation to when something is slow in the JVM to when some kind of event happened that is either in the VM or external to it. So to give you an example of an internal JVM event, that would be a garbage collection. So I'm almost always able to correlate a spike like this. Sorry, let me reverse that. I'm always able to correlate a garbage collection, especially if it's a big garbage collection, to a spike in JHiccup. But this can also be helpful for lots of other things. If your application is doing some kind of batch process internally within a running VM that is running other stuff, you'll see that come up here also, right? So again, what JHiccup does is it correlates when there's some kind of delay or pause within the JVM. You'll see a spike. There might be thread contention. You could correlate it, for example, to a large surge in traffic, and you may have some kind of deadlock around session objects or something like that, right? So again, this is by elapsed time, and what you do is you record when you started, so you get the exact time it started, and then from that you can derive what the clock time is based on the elapsed time and correlate that to something that's happening within your application or externally to your application. And again, the great thing about this is you can run this in production and it works with extremely low overhead. Basically, you're not adding any risk to a running application, which, as you know, when you run stuff on apps, when you run stuff on production, everyone wants to make sure that the thing doesn't blow up and cause more problems, right? Okay, so we already talked about this. We correlate to GC pauses and other events in the system or application. We need to map the Java app startup time to the clock time and then investigate. Okay, so check this out. It's called JHiccup. It's a free tool that's available from us, and it works on every VM, not just every JVM, not just ours. Okay, all right. So let's move swiftly on into coding practices because we have a grand total of 15 minutes, so this will be fun. All right. I will issue you a quick warning, though. And I think I've mentioned this before. As a software developer, we like to get down and dirty and get into the nuts and bolts of things, and sometimes we lose what our real goal is, right? Our real goal is to find a problem in the system or to find the bottlenecks or something is breaking on production or not running as fast as possible, and then we can spend hours or days looking at profiling data or this and that, right? And then eventually we'll get down to the code level and say, oh yeah, there's something wrong in this code. Let's go optimize it, right? But almost, I would say 80% of the time, it's not something in the code. Maybe 90% of the time, it's something else. But it's useful to know these code optimizations when you're actually writing code, okay? So again, this slide is a warning. It's great to get really complex in your code, but try to keep it as simple as possible. And I'll explain to you why that is in just a second. So let's look at a few of these optimizations and gotchas, okay? Now, many years ago, in the JVM, they came out with these wrapper objects, and then now we have things like generics, and we do auto-boxing and things like that, right? So, if possible, if you can use primitives rather than wrapper classes, that is super helpful in terms of performance. Of course, in Java, collections require classes, not primitives. So that adds a little bit of constraint in terms of where you can use primitives. But again, everything that I'm saying in the next few slides needs to be taken in the context of, do I really need to optimize this branch of code? You typically do not need to do this, for example. But if you're working in a bit of code that is doing a huge amount of data processing and you want to squeeze every ounce of CPU out of it, then you can do this, right? Now, the other thing around this, which I'll talk about quite a bit, is the JVM has something called a JIT compiler. The JIT compiler takes your code and optimizes it for you. So a lot of these optimizations will actually happen automatically for you by the JIT, okay? But again, if you have bits of code where you're worried about this is a critical path and it needs to be hyper optimized, that's when a lot of these things come in, okay? Some of the other things are kind of more stupid things too, like this one, string usage optimization. I can't tell you how many times I've seen this, both on projects that I've worked on in the past where I led the Perf team and with the Zool customers. A lot of people do the bad thing, which is the first block of code, right? You'll say string plus equals string plus string plus string. Now, this is the worst possible thing to do when you're writing code. Hopefully, everybody knows this, but if you don't, letting you know, right? So what happens is this creates a new iteration, it creates a new string in each iteration, but not just one string. You're actually creating two new strings and then a third string here, okay? So you're actually creating a large number. Actually, this I is an integer, but it has to be converted to a string. So you're creating 4 strings here. Okay. Now, the problem with strings is in Java, strings are immutable. That means once you create a string, you cannot alter the string. And once you've created a string, at some point it has to be garbage collected when you're not using it anymore, right? Which is very often, of course. So what you prefer to do in this case is you want to use something like a string builder, which goes and doesn't create a new set of strings every time you're going and doing any kind of string manipulation. This is probably if there's nothing else you get out of this, and if you don't already know about this technique, then thankfully you've learned at least one thing that's useful. Yes?
Doesn't compiler optimize this like to a string builder?
Okay. So the question is does the JIT compiler optimize this into a string builder also? And I hate to say this, but the answer is that it depends. It can do it depending on what the specific code is, but not always, right? And again, strings are immutable, and typically strings take up the largest amount of heap in almost every application that you see out there. So the short answer is not always, but it can, okay? And I'm going to do a second part of this in just a second, which hopefully will clarify that. Yes?
Is there also a difference between a string builder and a string formatter?
I believe the question is there a difference between string formatter and string builder? I believe the short answer is string formatter uses string builder underneath the hood. Okay? That's a good question, though. Okay? So anyways, strings are immutable in Java, so frequent modifications create many temporary objects, leading to performance bottlenecks. The more objects you create, the more objects that need to be garbage collected will actually put a whole bunch of stuff on the heap that need to be taken off the heap through garbage collection, which adds overhead, which you want to try to avoid. Okay? So let's look at this chart real quick. Right? Strings are immutable in Java. We talked about that already. But if you're wondering, should I use a string or a string buffer or string builder, this is a good chart to look at. The salient difference between string builder and string buffer is that string builder is not thread safe, but has the most performance. So if you're doing string manipulation and that string is not shared, it's in basically a single thread, then always use string builder. If you need something that needs to be thread safe, then you want to use string buffer. It has medium level performance. And then of course, just standard string is low performance because it's just a string, right? And trying to add onto a string is impossible. So adding a string and adding a string and adding a string creates a larger string, and then you have to dispose of 3 strings after that. Okay. So again, a lot of these techniques are around trying to reduce the amount of garbage or objects you create so that it doesn't have to be garbage collected. Okay. All right, so let's talk a little bit more about a few other things. Now, this probably goes without saying, but choosing the right data structure up front can save you a lot of headache and give you some good performance boosts. Use the right tool, in this case, right algorithm or right data structure for the job. So if we look at this example right here, what we have is I'm comparing an array list to a linked list here. I'm going to populate these, and then I'm going to do random access into an array list, and then a random access into a linked list. And you can see that I have big O notation here. Random access into an array list is O of 1. That means it's basically static, whereas random access into a linked list is O of n, so it depends on the size of the linked list. If you have a very large linked list, it will take a long time to do random access into it, as opposed to an array list. Doing access into an array list is basically static, or basically O of 1, okay? So when I ran this on my laptop, this specific example, the random access time into an array list was 2 milliseconds. For this specific test, you can see I did 100,000 times to try to tease out some good difference, or some the difference between that, whereas random access into a linked list was 5 orders of magnitude slower, okay? Now, you might be thinking, well, I'm not that familiar with data structures, right? And nowadays, you can cheat and just go to ChatGPT or Anthropic, and it'll give you the right answer 50% of the time. But if you want to learn about it, thank you for understanding that joke. So if you want to learn more about this and learn more about algorithms and how they can be better applied into daily coding activities, the book I actually recommend is not like some big, thick book on data structures and algorithms that you studied at university. There's actually a book called Grokking Algorithms. I believe it's by O'Reilly. Has anybody read that book, Grokking Algorithms? Yeah. So it's an excellent book that is well worth your read. It has lots of pictures in it. I'm a visual learner, so I like pictures. So check out that book. Again, it's called Grokking Algorithms, and it has a very approachable way of learning algorithms, and gives you a nice way to understand the difference between big O notation and big N notation. And if the big companies like Google were still hiring, you'd be ready for a Google interview after reading that book. So there you go. So no one's hiring anymore, apparently, but that's a different story to talk over beer. All right, so yeah, here's another quick example of the same continuation of the previous one. A linked list is good for frequent insertions and removals, whereas, and then hash sets are good for fast membership checking. So again, if you have a look at grokking algorithms, or you can find probably some nice tutorials on YouTube that help explain this, but I like to read instead of watching videos, because I can read faster than a video can put information in my brain. So anyways, check out that book, and in terms of, again, the right data structure and right algorithms make a tremendous difference when trying to write more efficient code, okay? So let's talk about a couple of different things here, right? And we're going to get a little bit into the JIT here. So let's say that we have some code like this. We have public static int compute. It's going and doing something, okay? It doesn't matter what. In this case, it's just multiplying, right? And then we have this loop that's basically stuffing numbers into an array, okay? Now, one of the things that I tell people is, if you can, try to minimize the method calls inside loops, because especially if you have a loop that's called many, many times, what you're doing in this case is it's not just the execution of that code that's problematic here. The problem is when you make a method call, what happens? Something gets put onto the stack with some reference data for whatever's in that call tree. So when you make a method call that calls another method, that calls another method, that calls another method, you're stacking things onto the stack, right? And when you do that, you're using memory and you're using compute time to be able to organize that call tree. Right? So I'm not saying that you should flatten everything into one giant 8,000 line method call, but if there are things that you can not have inside of a loop that you can just do inside of it, it makes a big difference, right? So this strategy is specifically called method inlining. Now, someone mentioned before about string builder. Oh, doesn't the JIT just do that for you? Well, in this case, the Java just-in-time compiler is actually very good at doing method inlining, okay? But for certain critical paths of code, it may be worth your time, it may be worth your time to inline those branches of code where you're always calling this thing many, many times inside of a loop, okay? But again, a lot of times you don't have to worry about it. It's if the block of code is being executed, a few times a second or a few times an hour or whatever, that's fine. But if it's a critical path of code that you're worried about in terms of overall throughput and performance, you could consider doing this. Again, the JIT will do this for you, right? It will eventually figure out that you're calling this method and it returns the same thing every time, and it will do what's exactly on the screen for you down at the bytecode level, okay? Now, that's great for us as Java developers, that the JVM does these kinds of optimizations for you, okay? Now, the only problem, maybe problem isn't the right word, the right word may be drawback, is that what happens? The JIT is not some kind of magic that knows your code as soon as you start your application. Your code has to execute, and your JIT has to look at what's happening and then determines what optimizations to apply. So what happens is it takes a while for the JIT to warm up and to optimize your code. Right? So on a medium-sized application, let's say you're writing a Spring Boot application. Let's just set some assumptions here to give you an idea of where I'm going with this. Say you're writing a medium, or you have a medium-sized Spring Boot application that's about 20 or 30,000 lines of code. How long do you think it takes for the JIT to reach, let's say, 95% code efficiency? The other assumption is that you're exercising all the code branches in your code, right? Your application is under load, so the JIT is able to see everything and apply optimizations along all the code branches. How long do you think it takes for the JIT to optimize, let's say, up to 95% of that code? Anyone want to guess? Right, again, the assumptions are Spring Boot application, 20, 30,000 lines of code. You have it under load so that it's exercising almost all the code branches. How long do you think it takes to optimize that?
4 hours.
What's that?
4 hours.
4 hours, that's a little bit too long. So it's not a bad guess, but it's a little bit too long. So typically in that scenario, it will take anywhere from 3 to 7 or 8 minutes to optimize it to 95%. But during those 5 minutes, let's say, your code is not running at optimal levels, right? So you may want to do a warm-up and then throw it in with more load or something like that. But you want to avoid that kind of complexity if you can help it. Okay, just a few more here and we're near the end. Optimized loop. So one of the things that we can do here, for example, is we can move invariant code outside of loops. This helps again, to make code run faster. And again, this is something the JIT will optimize for you, right? So if you do like a DTO object.get something inside your loop, again, what you're doing is you're putting something onto the stack and then popping something off the stack when you don't need to do that necessarily. And again, you don't have to obsess about this. You shouldn't go through and rewrite all your code in this way. The JIT will do this for you, but for critical paths of code, it's worth thinking about something like this. Okay? And I don't even want to get into synchronization. You probably understand some of the pitfalls with synchronization, but there are ways to basically don't do synchronization and as much as possible. Try not to have shared objects. Those typically tend to be the biggest bottlenecks I see when working with customer code, is that they're doing synchronization when they can use other techniques to not do synchronization and have blocking calls within their code, right? Sometimes you have to do it, of course, but if you can avoid it or externalize the synchronization or do eventual consistency for synchronization, that will help performance dramatically within your code base. Okay. And of course, I have to insert my joke about regular expressions here, right? I had a problem that used regular expressions, and now I have 2 problems. But one technique that is actually quite useful, and again, the JIT can also do this for you, is doing caching of regular expressions so that you're not compiling a regular expression every time you use it. You should compile a regular expression once and then use it over and over again instead of compiling it over and over. Okay, so this is what the code for this looks like. Okay, so I am 2 minutes over time. I'm going to try to wrap up really quickly. There's not much to say about caching except for a few things. Did anyone get the reference here? Okay, good. I'm glad somebody did. The well-known technique for better performance, everyone's familiar with it. Things like JP and Hibernate use caching. And there's lots of different reasons to do it. There's a lot of different techniques like lazy loading, cache aside, cache preloading. I see a lot of people do cache preloading, which is basically instead of letting a cache populate over time, when the VM starts up with your application, you preload the cache so you start with maximum performance right out of the gate. Another technique that a lot of people do is caching is not just for databases. You can use a number of different tools to have different types of in-memory caching, which is super useful. Again, you don't need to do this for everything in your code base. It's good for where you have a critical path of code that needs low latency and high throughput. And there are different caching loops that you can use. There's Memcache, Caffeine, Redis for distributed cache. Hazelcast is also popular for caching. Okay, so let's talk about memory and garbage collection. I know we don't have much time, but what I want to do, since we don't have a lot of time, is I want to leave you with a diagram that you can look at afterwards, and you can say, yeah, this is probably the right kind of thing that I should look at in terms of garbage collection, right? Right-sizing JVM heaps is extremely difficult. You probably know this because you probably have done this. What does right-sizing mean? How big should my heap be? Should it be 16 gigs or should it be 512 gigs, right? How much caching am I doing in memory? How much load does this thing take? How big is my microservice? All those things play a big part of this. Now, I will say when it comes to garbage collection, and once you've figured out how big something should be, G1 GC is typically pretty good for almost all applications. There is really no reason to go down the rabbit hole with something like this. But a pauseless garbage collection can be great for low latency and high throughput applications. There are some pauseless garbage collectors. There's a free one available now in Java 21 called Z1GC. And then Azul, in our high-performance VM, we have a very high-performant pauseless garbage collector called C4, right? But that's in our high-performance VM. So again, it's a pauseless garbage collector. This is not useful for you if your heap size is 32 gigs. If your heap size is 64 gigs or 128 gigs or multiple terabytes, then a pauseless garbage collector is probably a good idea. But if you're running with a small heap, nowadays on modern hardware, you don't need to have a pauseless garbage collector, right? Don't tell my salespeople at Azul I said that, by the way, okay? They won't like that. So anyways, good for large heaps. Again, everything in software development and architecture is a trade-off. Having a pauseless garbage collector is not 100% free. You do need more CPU resources to be able to have that pauseless garbage collector run efficiently. So it does require more GPU. So you're trading off a little bit more, CPU for more lower latency and more stable garbage collection, basically zero pause time. Okay. And again, I already mentioned this. We have the best garbage collector in the industry, C4, but there's also Z1GC. And this is the diagram I wanted to leave you with. Okay. So this is a diagram that was done by my colleague Garrett, who's giving a talk later today. I recommend you go see his presentation. He's going to be talking more about code inventory and about like reducing technical debt and getting out dead code. But if we look at this real quick, you can see that, for example, if we look at like C4, which is a proprietary garbage collector, if we look at the throughput and latency, you can see you get very low latency and high throughput. Similar for the open source ZGC, sorry, not Z1GC, ZGC. But there's a number of different ones, and here's the G1 garbage collector that we were talking about. And again, as a software engineer, I like to go and get my hands dirty with this and play around with all this stuff. Do you really need it to change garbage collectors? Probably not, but if you see that there's an issue with this, your first port of call is to take some GC stats. We actually have a really good tool called GCLA, or Garbage Collector Log Analyzer. It's a free tool that Azul provides to the community. So you turn on extended garbage collection, basically debug garbage collection metrics, so it'll spit out the different things, the garbage collector and how often, and what are the different survival spaces. And the GCLA will help you analyze that. There are other tools that will help you analyze a garbage collection output, but that one is free and it's pretty good. Okay? And so we are at the end of our session. There's some links here. This is how to reach me. And I am 5 minutes over time. So please don't downvote my session because I kept you from lunch. Okay, please. I hope you enjoyed it. Happy to follow up with you.